Okay, so in this video, we will consider the following example, which hopefully will convince you of the full power and beauty, just pure beauty, of the fundamental theorem of calculus. So here's the question. We want to find the area below the curve y equals negative x squared plus x plus 6 on the interval from negative 1 to 3 using A, Riemann sums, then B, our knowledge of the fundamental theorem of calculus. So we're asking to solve the same problem in two different ways. Hopefully in both cases we'll arrive at the same answer. Well, let's get a feeling for, again, the geometry here. So let's sketch this curve on the interval from negative 1 to 3. You can find here, of course, the apex of this quadratic, finding the derivative, setting it equal to 0, giving you the sole critical point of this curve. But here, as you'll notice, this is easily factored, and by finding the zeros and noticing we have a negative quadratic term, this will be a parabola facing downwards, and having the zeros will allow us to sketch the graph very accurately over this interval. So let's just factor it. So y is negative x squared plus x plus 6. Factor the negative sign out of the whole expression, which gives you x squared minus x minus 6. And now let's try and factor by inspection. We are looking for two real numbers whose product is negative 6 and whose sum is negative 1. Well, this is obviously negative 3 and positive 2. Negative 3 times 2, negative 6. Negative 3 plus 2, negative 1. So we have the factorization. So the zeros are x equals 3 and x equals negative 2. So now we have a very simple way of sketching this quadratic. Let's go from negative 2 to 3, both zeros. So as I've said, we have a parabola facing downwards, and we have the two zeros. X equals 3 is one zero, x equals negative 2 is the other 0. And if you did find the apex, you would find that it would be at 1/2. Let me just try and sketch this parabola. It should be symmetric. Again, slightly crooked picture, who cares? And again, we want the area below this curve, which we can see between negative 1 and 3 is positive. That's what we want, the area below this curve on the interval from negative 1 to 3. So we're asking to find this area in two different ways. Well, first, let's use Riemann sums. As always, we need essentially to do three things before we can play with the sum. First, what is our delta x? So this will be solution A. Of course, the same picture goes for solution B. Delta x is b minus a over n. B here is 3. A is negative 1. So 3 minus negative 1 is 3 plus 1, 4. So 4 over n. We need xi. Xi is a plus I delta x. A is negative 1. So negative 1 plus I times delta x, 4 over n. But I'll do as always delta x times I. So 4 over n, times I. So we have our xi. And of course then we have to compute and simplify f of xi. Well, we are making as always a simple substitution. F of x is negative x squared plus x plus 6 for any choice of x. We are now replacing x everywhere by xi. So we'll get negative xi squared plus xi plus 6. So let's replace. Negative this squared. Positive xi, so plus this, so minus 1 plus 4 over n I, positive 6. Let's square this. And I'll square and negate at the same time. So negative 1 times negative 1 plus 1 being negated, negative 1. Negative 4 over ni, twice of that, is negative 8 over ni, once again negated, positive 8 over ni. And finally, 4 over ni times itself, 16 over n squared, I squared, negative of that, negative 16 over n squared, I squared. Finally, negative 1 plus 4 over ni plus 6. And now we can regroup similar powers of I and the constant terms together. Unique quadratic term, negative 16 over n I squared. Multiples of I, 8 over n plus 4 over n, 8 plus 4 is 12, so plus 12 ni. Constant terms, negative 1, negative 1, negative 2, plus 6, positive 4. And now we have all that we need. Delta x is 4 over n, f of xi, negative 16 over, over n squared, I squared, positive 12 over ni, positive 4. And now we're good to go. We can set up the area as the limit of the corresponding Riemann sum, and then evaluate the sum simplifying, and then letting n go to infinity. So A equals the limit as n goes to infinity, summing from the first to the nth rectangle, the height of the ith rectangle times the width. We can now replace. We have f of xi fully simplified. Of course, times delta x, which we found to be 4 over n. Alright, at this point this should be very routine. Pull out the constant with respect to I out of the summation. And again here I will do two things. If you factor this out, then you have the sum of these terms plus these ones plus these ones. And we can distribute the sum over all three. So we can sum these plus sum these plus sum these. So I'll do this at the same time. Okay. Second step, or third step, factor all the constant terms with respect to I out of each summation. So negative 16 over n squared out. Twelve over n out. Four again, 4 times 1, factor 4. That leaves you with the sum of 1 as I goes from 1 to n. And now we have our first three fundamental sums, right? So we can replace each one by the corresponding expression. if you sum I squared from 1 to n, so this is 1 squared plus 2 squared plus 3 squared up to n squared, we know we can bypass the sum, and the formula is n times n plus 1 times 2n plus 1 all over 6 plus 12 over n. And if you sum I from 1 to n, 1 plus 2 plus 3 plus 4 up to n, we can also bypass the sum with the shortcut formula n times n plus 1 over 2. The last one is trivial. If you add 1 n times, 1 plus 1 plus 1 n times, that's just n. Okay, we're getting closer. I will recopy this line on the next page. Or actually, yeah, let me do this. It'll be easier. And we'll just pick up from there. Alright, so it's recopied. You can keep going. As always, we'll simplify first the n's. So in n over n squared, we can cancel one of them, top and bottom. N over n goes away. So that takes care of the n's. We can simplify then the constant terms. 12 over 2, well, that's just 6. 16 over 6, well, we have a common factor of 2. Factor 2 from 6, you get 3. Factor 2 from 16, you get 8. That's it. Now, leave the 4 outside. It's a constant multiple. And we will put the constants together and then bring the 1 over n in this expression. So multiplying every term by 1 over n. So what are the constant terms here? Negative 8 over 3. We have the n plus 1 over n here. And of course, we'll put the 1 over n with the 2n plus 1. As we always do. Here we have a single plus 6. Single n plus 1. If you bring the times 1 over n, you'll have n plus 1 over n. And here this will be trivial. 4n times 1 over n. 4n over n. And as always, we are now 2 steps away from being done. We divide through every term by n. So what does that give us? N plus 1 over n. 2 plus 1 over n. Whoops, not n. N over n is 1. So it's 1 plus 1 over n. Sorry about that. Then 2 plus 1 over n. Plus 6 times n over n is 1. So 1 plus 1 over n. N over n is 1. So plus 4. And now we can let n approach infinity as we have a trivial limit. 1 over n goes to 0. And what are we left with? Well, 4 stays 4. Then we have negative 8 thirds times 1 times 2 plus 6 times 1 positive 4. And now we just simplify. So 4 times, well, negative 8 times 2, negative 16. Negative 16 over 3. Plus 6 plus 4 is plus 10. But 10 is over 3, 30 over 3. So what do we have here? 4 times. Well, 30 minus 16 is 14, so 14 over 3. No common factor between 4 and 3, so we multiply 4 and 14. 4 times 10, 40. 4 times 4, 16. 40 plus 16 is 56. So we finally get 56, over 3. You say, woo! We catch our breath. Alright, so what did we find again? If you go back, this was the, go all the way back, right? Scroll up, keep scrolling up. We had the area below our curve. We had found A, so the area below the curve, y equals negative x squared plus x plus 6, between x equals negative 1 and x equals 3. So the exact area of this region we have just found using the limit of a proper Riemann sum to be exactly 56 over 3. Woo! Alright, that's part A. Well, if you remember, in part B we were asking the exact same question. We're going to find the area of the exact same region. Instead of now using Riemann sums, we want to use the fundamental theorem of calculus. And we'll see if we get a more elegant and also shorter solution. We'll see. So again, as we have just said, we want the exact same area, but since f is positive, the area is just a definite integral from negative 1 to 3 of f of x dx. And our function was negative x squared, positive x, positive 6. And now we're good to go, right? When you have a positive function over the interval, the definite integral of this function over the interval gives you the area below the curve between x equals negative 1 and x equals 3, which is exactly what we want. Of course, now we're going to stay away from Riemann sums and use the fundamental theorem of calculus. What does it say? Well, it says first, find the indefinite integral. So find an antiderivative to your function. And once you find this antiderivative, evaluate it at the two endpoints, negative 1 and 3, and then subtract both values. Okay. Well, this is a pretty easy function to find the antiderivative of. It's a polynomial, use the power rule. Negative x cubed over 3, positive x squared over 2, positive 6x. And again, you can take 5 seconds to check. Take the derivative of this function, and you will get the original function. So here's our antiderivative. If you remember, we don't need to add plus c, as when we evaluate at 3 and negative 1, c stays plus c. When we subtract, it just goes to 0. So we don't need to add plus c. So, first step of the fundamental theorem of calculus. When you want a definite integral, find first the antiderivative, check. And now we just calculate our antiderivative at both endpoints, and we subtract. So we evaluate this when x is 3. Well, 3 cubed is 27 over 3 is 9. So we get negative 9 plus 3 squared is 9 over 2 plus 9 over 2 plus 6 times 3 plus 18. So that's the value of our antiderivative at 3. Let's evaluate at negative 1. Negative 1 cubed is negative 1. Negate that, you get positive 1. Negative 1 squared is 1 over 2 positive 1 half. 6 times negative 1, negative 6. And of course, the fundamental theorem says, or this notation, the value of the function at x equals 3 minus the value of the function at x equals negative 1. And now we just calculate this. So what do we have? Well, negative 9 plus 18 is positive 9, so we get 9 plus 9 over 2. Then, minus a third, minus a half, minus negative 6 plus 6. Let's be clever about this, how we calculate this. 9 plus 6 is 15. 9 half minus a half, well 9 minus 1 is 8, 8 over 2 is 4. And of course minus a third. So all we have now is 15 plus 4, 19 minus a third. Put all over 3. Well, 3 times 19, well 30 plus 27 is 57. 57 over 3 minus 1 over 3 gives you, 56 over 3. Would you look at that? I'll give you a second to take this in. Look at how nice this was. How slick, how short, how elegant. This is almost too good to be true. Right, look back to your previous solution and go back how we found the exact area below negative x squared plus x plus 6 between negative 1 and 3 to be exactly 56 over 3 with Riemann sums. This was a lot of work, right? It was really a lot of work. With the fundamental theorem of calculus, it's really just 2 steps. Find the antiderivative. That's basically trivial for a polynomial. Evaluate at both endpoints. Very easy. Little subtraction, and we're done. And that is why we love the fundamental theorem of calculus. Not only does it connect two seemingly unrelated notions, the notion of area with the notion of antiderivatives, but by bypassing the Riemann sum in favor of the antiderivative, it produces much shorter, much nicer solutions. So hopefully now you have a better appreciation of the fundamental theorem of calculus.